everyone, and welcome back to Physics 4A. Today we are going to go through motion in 2 and 3 dimensions. So if you remember last week we talked about motion in 1 dimension. Now we're going to expand that to 2 and 3 dimensions. Alright, so the first thing I want to go over is the position and displacement vectors. The position vector is the vector from the origin of the coordinate system to some point, P, and it is r of t, okay, r bar of t we can say. And it looks like this if we're looking at it in a graph. Okay, so we have our 3 dimensions here, x, y, and z. This is typically how we will set it up. And if we have some p, point P, our vector will be from the origin to that point. Okay, so it'll point towards the point, and that will be our position vector, okay? And we can describe it in our coordinates as so. So we have our 3 positions, x, y, and z, and they all depend on time, okay? And our unit vectors here, I, j, and k. So this is typically how we will write our position vector, okay? Now our displacement vector is going to be between 2 different points, just like this graph shows you here, okay? And so we have 2 different position vectors, and so our displacement vector between the 2 will be our delta r bar. Okay, so this is how it is defined graphically. And so we looked at something like this last week, but again, only in 1 dimension. Okay, so this is how we can look at it through 2 and 3 dimensions and through vectors. All right, so we need to start with an example. This is example 4.1. It states that a satellite is in a circular polar orbit around Earth at an altitude of 400 kilometers, and it passes directly overhead at the north and south poles. What is the magnitude and direction of the displacement vector from when it is directly at the North Pole or over the North Pole to when it's at a negative 45-degree latitude? Okay, so we need to make a couple notes here. So it says it's at 400 kilometers altitude, right? But that is just above, the Earth's surface. Okay, so this would be like 400 kilometers above the North Pole, right? That would be its orbit, okay? But we need to take into account the radius of Earth. Okay, so I'm going to draw a picture here, and it's going to be not great, but I'm trying. Okay, so this is our x direction, x direction. This is our, y direction. Bear with me, sorry about the bad drawing. So this is our x and our y directions here, okay? And this is our Earth. We're pretending we're kind of like we sliced into it and we're looking at a cross section of it, okay? And so our orbit is 400 kilometers above the Earth, okay? But when we're doing any kind of mathematics with this, with a circle, we know that we also have to take into account the rate. Wow, that was an interesting thing there. Hold on. Let me erase that bit. Okay. We need to take into account the radius here. Okay. So we can't just start calculating things with that 400 kilometers. Okay. So the radius of Earth, I'm going to label it that way, is 6,370 kilometers approximately. Okay. So our total radius that we will be looking at will be 400 plus that 6,370 kilometers. So we have 6,770 kilometers. That is going to be our radius from the Earth's center to where our orbit is. Okay? Okay. So that's the first portion to kind of note. Next, we want to find out this other vector. So this is our first vector. We can call this R1, okay? And then our next vector is going to be when the satellite is at negative 45 degrees latitude. So that's going to be from the x-axis here. So I'm going to estimate 45 degrees about there. Okay, and this is, again, at the same radius, right? Our radius is the same, but the vector direction is not, okay? Okay, so this is going to be called R2, okay? And then our displacement vector, which is what we're looking for, is going to be from the North Pole to this other point at negative 45 degrees latitude. So this is a very poor drawing. There's a better drawing in the book, but I'm trying to show you guys that you can draw these examples yourself, okay? It's a little difficult on a computer to draw this stuff. All right, so this is our displacement vector. It's going to be delta r bar, okay? So this is what we're looking for. This is our big question mark, okay? All right, so now that we kind of have an idea of what we are looking at, we want to determine our, first of all, our two vectors that we have initially. So R1 is only in the y-axis, okay? So it doesn't have any x component. And the magnitude of it is the radius here. So 6,770 kilometers. And again, it's only in the y direction. So I'm going to call that j hat, okay? And you could note the units if you want. I may not carry them all the way through, but make sure you understand where the units are coming from, okay? R2 bar is going to be a little bit different because it is not on an axis. It's not just on the x-axis or just on the y-axis. So we have to figure out how we can describe that, right? So, and we looked at that in our first section with the math and kind of getting reminded of the calculus and stuff. So, in our trigonometry identities. So this will be described as 6,770, okay? And if this is our theta, or our negative 45 degrees, we want to know the x-axis first. So we can say that's going to be adjacent, right, over hypotenuse. So it's going to be cosine of that negative 45 degrees. And again, that's our x component. So it's going to be I hat plus the same value. And it's going to be now opposite over adjacent. So sine negative 45 degrees j hat. Okay. So now these are our two starting vectors. Okay. And we can rewrite this one just a little bit. Okay, we can take this and put it into our calculator and we'll get about 4,790 I hat minus 4,790 j hat. Okay. So now what we'll do is we'll go ahead and find our displacement vector. So remember that that's going to be r at t1 minus t2, r at t1. Okay, it's going to be that difference there. Okay, and these are just the same as saying r2 and r1. Okay, I just shortened it a little bit. So we'll take our numbers and I'll plug them in. 4790 I hat minus 4790 j hat minus our R1 or RT of 1, 6770 j hat. Okay, and we get 4790 I hat minus 11,560 j hat, approximately. Okay. Now we wanted to know the magnitude of this. So our magnitude is going to be the square root of these numbers. So 4,790 squared plus negative 11,560 squared. So all of that square root. And we get a magnitude of 12,500 kilometers approximately. Okay, so this is our displacement. So that length there, that distance there, okay, between the two vectors. And then we wanted our direction, so I'll call that theta. Okay, the direction at which this is, so that's going to be tangent inverse of negative 11,560 over 4,790, and we get negative 67.5 degrees. Okay, so this is our direction of our displacement vector and our magnitude of our displacement vector. Okay, so this one may have seemed a little bit tricky, but not too difficult once you get through the math. Okay, all right, let's move on and look at another example. This one is basically talking about Brownian motion, which is a random motion of particles. Okay, and so it describes it here, but we just want to say, okay, we've got this particle and it moves around from the origin, and we want to find the total displacement from the origin. Okay, now as you can see, we already have a few different displacements that it describes, and so we want to find the total displacement. Okay, so our total displacement, delta R, you can say total if we want, is going to be the sum of each individual delta R. Okay, so we'll take all of these values and add them up. So our total displacement is going to be, and what we can do is we can kind of group them in terms of the direction if we want. That might make it easier, or if you can just look down the line and do it in your head, that's fine too. So I'm going to go ahead and group them. So it's going to be 2.0 minus 1 plus 4, I'm going to drop the zeros, minus 3, and that's in the I direction, plus 1j, this one has 0, this one has a negative 2, and this one has a 1, j, plus, I'll go down here, 3k plus 3 plus 1 plus 2 k hat. Okay, so now we can add them all up, and we get 2i plus 0j plus 9k. So this is our total displacement vector. Okay, we don't have to write the 0 here, it doesn't really matter. You could just say 2i plus 9k, and that's completely fine too. All right, I'll continue on the next video.